that we have a inclusion from the lower limit to the upper limit of the system, right? Lower to upper. This function is defined for that range, right? That's how we typically think about it. We say this function works for those values. So if I was to plug something into this from a generative prospect, I would say this function could create those relative outputs, right? What am I describing? I'm describing that the instructions or the system of materials are available in that value set. So let's say that we have a certain individual. We have their height and their weight, right? Because one of the things we were looking at or thinking about previously, right? Just the idea of something that's not 100% consistent from individual to individual, but there are certain underlying factors that correlate those things together. So if I was to start putting some values on this system, right, where do they occur? They tend to aggregate towards the mean of this space, right? Just the generalized notion of average values, right, tends to indicate that things are going to kind of work typically towards some normalized distribution, all right? When I say that the data set captures information about the material being provided, right, the effective communication of this data set is what? To correlate those particular features together, to provide something that describes the underlying process. The argument given here is that it is only a fully informative or maximally informative data set when all the values that are possible, right? We notice we've got a value right here that's right up against the upper limit, right? But there's quite a bit of space in here where we don't actually have any values represented. But because of the fact that I have a value that's edging up against the top possible value in that space, I've done a pretty good job at describing what is possible with respect to that space. Let's think about it from this perspective. If this distributional characteristic has this mean, right, and it has this standard deviation, then we say that information about this system is going to be prescribed based upon the spread characteristics such that the square of that standard deviation provides us with some idea of how far out from that mean relative to the shape of that distribution exists, right? How much information exists in that edge space, what the relative span of that information is. So the term variance here is describing the relationship of how the values change on average as you're spreading out to the minimum and maximum for the available function. That is the principal argument of principal component, in the effect that saying, if I have a projection with 2 dimensions of data, right, and I have points that are given by these 2 dimensions of data, then if I only want to keep 1 dimension out of those original 2 dimensions, effectively operate as a recombination of those 2 initial features, then the only thing that matters is the preservation of the maximization of variance in that system. The more varied that system is, the wider the space over which the values are projected on that new space differentiates in each individual example from each other individual example such that it maximizes their informative quality, right? The further away this guy is from the mean, the further away these are from one another, right? The more relevantly informative this data set becomes because of the fact that it implies to us that there are potential values within that space. We talked previously, this is a concept of entropy. Entropy is the notion that all of the values that are possible are at least represented within the data set. So if we want to maximize the representational power of that data set, i.e. its descriptive characteristics, right? What would be optimally descriptive? Would be a set of information such that we have a function that provides us with the full range of possible values that it can assume, at least to some degree. It doesn't have to be 100% filled within this space, but the full range must be expressed, right? Or at least as much of the possible range must be expressed. So let's look over here just real quick at what we're looking at this edge. What is the likelihood of any value to fall within this space? Really, really tiny. However, it can happen. So what happens if my data set doesn't include it? I didn't actually give you that full limit. I gave you something that is less than that limit, right? This is effectively L minus delta. L minus some value, right? I don't actually have a value that expresses the full range of the system. So what am I actually going to assume? I'm actually going to assume it stops there. Because of the fact that nobody's told me it could be less, my data set only includes that could be that value. I'm only going to model it over that range, right? So because of the fact that I have less information, I have been given less information by this system, effectively, I imagine this whole chunk of it doesn't even exist. And I actually model the distribution such that I assume that that's the minimum value of the system.
Okay.
Yes?
So initially you were doing the lower limit as like negative infinity, upper as infinity. You look at the data set, whatever the lowest value is and potentially the highest value, that's where you're going to do the cutoffs.
Make better sense?
Yeah.
I knew. That's the dumb part of this class. I put a hat on it and everybody goes, oh. It's hilarious. It really is. I love the notation for this sometimes. What you're saying is, for the real f of x, the real f of x is bounded negative infinity, positive infinity. That would be the real definition of a true normal.
Mm-hmm.
But once I put the hat on it, I say, look, I can only work with what I've actually been given. Right. So now the inference version of this system is my guess, my estimation function, valid only for the range as prescribed by the relative amount of variance captured by this particular vector. And I say captured because of the fact that I have a variety of different linear recombs that I can draw through this system, right? Which one do I pick? Each one has a certain amount of a balance between x and y, right? Each one, whenever I reproject the range of the values of the system on it, right, is going to have a slightly different set of characteristics with respect to how wide, how relatively varied the distributional characteristics are. If I take the points that I have and I project them over a maximally long space, right, a maximum variation within that vector, I've captured as much of the information within a single dimension as it is possible to do. This is the cool part about this. That's a fact-driven statement. Many of the things we've talked about beforehand are like inferences or estimations, whatever. We look at this and say, I can't draw another line that does any better. Period. That's it. That is the best line. Guess what it doesn't need? Labels. It doesn't need to know anything about the classes of the output. Why? Because I've got the maximum variation. That additional bit of information does not help me in capturing variance with respect to the inputs. Only inputs, only the feature values matter in capturing maximization of variance. So what's the other cool thing that you get to do with respect to PCA? You get to use all of the data because you can't bias it. You can't bias it. We were previously doing this how? We were doing it based upon the quality of the line, right? So the quality of the line to produce a set that differentiated between the two classes, right? I don't have class information anymore. Now I'm just looking at thinking about some theoretical combinatoric probability distribution with respect to the feature characteristics, regardless of which class they're in. And I'm saying I want a new feature that recombines those characteristics over the maximum space. What does that argument take into consideration? Only one part of the original linear discriminant algorithm, only the LDA. Guess what it says? Maximization of within-class variance. Previously, we were attempting to minimize within-class variance, right? So maximization of within the distributional variance effectively should do what? It should spread the two classes out as far away as possible from one another. That's already handled. We already handled it by projecting it on as wide of a possible space. Variance changes with respect to what? Variance as defined is the expectation of the square minus the square of the expectation. So things, as they spread apart from one another, as they get higher intensity, will get further from one another if we maximize the variance of the projection. So discrimination, being able to tell the difference between two things, will be best when projected onto a larger space. Are any of you familiar with how analog to digital conversion systems work, ADCs? Yes. Think about the operation to be able to discriminate between one value, between one voltage and another voltage, with respect to the levels of an ADC, how many bits you're planning to use, right? So an 8-bit ADC will represent something for 256 unique values. So if we have, let's say if we have a range of 0 volts to 5 volts, and we have 256 values within that range, right, 0 to 255, can I discriminate between something like 1.1 volts, right? There's a point in there, 1.1 volts and 1.15 volts? Nope. Nope. Why?
Oh,
I don't have enough bits. Right? I don't have enough bits. So here's the consideration. What are we thinking about with respect to that value up above? The bits of the ADC, the new discretization of the register is effectively the variance that is represented over the range prescribed here. Extend this to a 10-bit system, I get 1,024 values, right? Now I can make the distinction. By taking into consideration the minimum required variance to make the level of distinction, I can prescribe the number of bits that are required in order to be able to differentiate between to have the granularity between the 2 points that I'm interested in. This is the idea of resolution, to be able to discriminate one thing from another thing, to resolve it, right? To create, what did I just put in there? I said to divide between them, right? But what do we look at that? That's a discriminant function. It's a linear discriminant, right? I say, what is the required variance such that I'm able to adequately discriminate between the elements? So let's say that if we make sure that we maximize this, if we always maximize it, will it always be able to tell the most possible information between the items? We'll be able to obtain maximum differentiability? Yes, with respect to that consideration. If the number of bits is the maximum that I can obtain, then what? My differentiability will be maximized. I can always make the argument that I can't have done any better with what I had other than the maximization of variance with respect to the area or the range over which the values were projected. The idea is that the axis here does what? Maximizes the range over which the values within the set could be projected. Here's the interesting part. What do the values on that line represent? What do these mean? So let's just zoom in here. This is what happens when we actually take the principle, right? Notice we've got all the individual little lines there. What does that look like in some senses? It's the hypotenuse of the square that we utilize to calculate RSS, right? So if I was to take the square of this point, right, the square of this system, take a right triangle created by the RSS and take the hypotenuse of that triangle, and you have the projection onto that line effectively. It's normal to the surface of the line. So what does that mean? Once I establish the maximization of the variance with respect to that RSS, I've maximized the variance of the projection space of the system. Now I take that rotation and do what? I apply the rotation to the entire system. So I originally put the line through, and I had the slope for it. The slope implies rise over run. Effectively, I apply a rotational transform to the system such that the new horizontal axis in the system is the projected axis for the maximum variance projection. That's what's going on over here, right? I took the whole thing and I rotated it. We did this with LDA, so it's really similar to the LDA in the effect that I crank the system around it, I move that line until it finds the optimal projection, the maximum range, the maximum variance within the system. It's not entirely the maximum range of values, it is the axis that maximally differentiates the individual elements from one another. That's the reason why the term, or why the value used there is variance, the square of the differentiation. You have a question?
So since we're maximizing the variance and bias isn't a concern, does this solve the trade-off issue?
There is no trade-off.
There is no, so, okay.
No, I
we
don't
have to worry about trade-off.
Previously, the trade-off was bias to variance, right? Is that variance the sigma square? It is in a entirely different way. I don't like to go into that part because it doesn't really make sense, all right? So you have to really go round in its barn to get to the way in which those two variances are the same. But what do we mean by something having a variance whenever we talk about the bias variance dilemma? We talk about their...
Is it flexible?
Yes, but what does that flexibility cause? That flexibility is not directly linked to one numerical coefficient. It's linked to a differentiation between the performance in the training and the performance in the testing, right? So we say that the variance is data set to data set performance variance, right? I know we use the same term for it. The reason why I say I wish that there was another way to say it, but I have to explain it to you the way other people use it. And I think that there's this, just like jazz or any other, like niche thing, once people get used to their little vocabulary, they like to know they're the only ones that can talk about it, okay? Right? We know how to use variance. I don't think you know how to use variance, So it's like, oh, we have more than one definition for variance. It's contextual, If I'm talking about performance variance, that's different than the relative differentiability. But in a sense, it's similar. Let's think about it. The differentiability with respect to an individual feature is taken with consideration of maximization of variance. So if we're to think about a robust model, we would say that that is the model which describes the underlying system such that it would be maximized in its capacity to work for any given data set that's sourced from the same original function. If f of x is the core function, the real generative function, if it's gravity, right, the true underlying universe level principle that's driving this system of orbits, right, when we model it, then I should be able to take any solar system and any stellar body orbiting around anything else, and I should be able to apply the same function approximation to that system and have it work. If it varies from solar system to solar system, I've either overfit to one solar system or I've underfit in general, right? So we look at it from the perspective of saying underfitting means I haven't adequately described the relationship, I've been too simplistic, or I've overfit with respect to I've made it too solar system specific to be able to adequately describe the true underlying system that is working within that space. That variance, the bias variance dilemma is, how well does it work on this solar system? That's the bias, right? You say, the better it works on that system, the more I eat away at the error, right? Eat away at the error, I technically am going to reduce bias, right? Bias and error in that sense can be thought of as being mutual. I think I've mentioned that beforehand. I try not to say that early on in the process because I don't want people to get confused about it. Because bias does refer to error only within the training set. It's like training set error, right? So the system becomes more and more biased when its training set error is reduced and effectively continues to reinforce its biases. It already had a pre-existing notion of what should happen. It may have actually arrived at the pre-existing notion of the true underlying system, and then it kept going, right? It kept going. That's when we talk about the real dilemma of attempting to try to globally minimize bias, right, what happens is we tend to cause an increase in set-to-set performative variation, right? So from training set to testing set, our performance starts to be varied. You could actually look at it from, the reason why we say it's varied, when we think about strictly binary, training, testing, right? Think about k-fold cross-validation. Which one's training and which one's testing? It varies. It varies. I think that might be part of the reason why they utilize that terminology, right? There's a train test variance, model-to-model variance, with respect to how well that's on its localized internal testing set, right? But since everybody is a testing set at a different time, it varies as to who is describing what performative characteristic. So this idea of variance is to say that we're maximally spreading these values out over this system such that it's like getting the butter nice and, nice and warm so that it spreads out really well over the piece of bread, right? We're going to orient the piece of bread so that it spreads evenly, spreads optimally over that space, such that every given point is effectively as far away from any other given point as possible. The idea is that maximizes the values with respect to their descriptive capacity. We've gotten everything we can. We've squeezed the lemon until there is no more juice left. At this particular angle, this is the optimal angle for squishing it to get everything out we can. We're going to have to turn it again to get the remainder out, okay? That's the argument. At this angle, we've squished all we can out of it. So what happens here is we apply the rotational transformation, and now we see what? We see that most of the data, right, most of the variance, the spread over which that value is now representing, is contained, a good chunk of it. Let's say that originally, half of the information, originally, let's go back here. Let's say that functionally, I can make the argument that half of the information is contained in population and half in ad spending, right? I could try to make that argument. What would be the requirement? A lot of people answered the question for certain pre-assumed certain assumptions, right? Certain presumptions made with respect to linear discriminant analysis. One that we made frequently was what? Equal priors, right? Equal priors. What do those equal priors imply? Equal variation for each of the classes, right? Their spreads are the same in each of those cases. The argument would be here that if the spread in population relative to the spread in ad spending were equivalent to one another, then the axis of maximum variation, right, the angle of projection for the principal component, the linear recombination of features with maximum variance would be what? Exactly a 45-degree angle, because it would take half the information from population and half the information from ad spending. This would technically be the worst possible principal component you could come up with. Why? So let's imagine that 70% of the value is actually contained in population, because I think that's maybe true in this particular case, right? The lower limit of the system is something like 19 to upper is something like 60, right? So we have 50-some values, or a range of 50-some values over which population is represented. Ad spending goes from something like maybe 1 or 2 all the way down there at that 20 mark, all the way up to about 30, right? So it's a little less total range of values. There's a little less variance with respect to the values that are represented in that space. So let's say that this is 70-30. Does the reprojection contain all of the variance of population? No. Why? Because if you were to think about this as a vector going in this direction, right? Think about what happens when you raise the vector up this way. Now, the length or the run over which that value is represented, some of it is in rise, some of it is height. So if you decompose those vectors, right, originally you have the length of a vector, now you're representing it as a hypotenuse of the system. This is effectively less of the total spread of the original system. However, what is it doing? It's capturing some of the spread of ad spending as well. Matter of fact, it's capturing the maximum amount of ad spending and the maximum amount of population that can be put into a singular vector. So let's say that this is 70% of the information, and that's 30% of the information. The idea that would be that I would keep something like 60% of the original pop, right? And then maybe 18% of the ad spending data. Cumulatively, I've done one. I've gotten more than the original 70% of the total information in a singular vector. I might have gotten something like 80% of the total variance within a singular vector. How do I know that I've captured the variance? Let's look at this. So originally, right, you have a horizontal spread and a vertical spread, right? Horizontal and vertical spread are shifted and pushed across both of these original projection vectors. Now that I have them pushed into the new principal component across the horizontal axis, the spread or the variance across the first principal component is just a one-dimensional variance, right? It's not spread in two-dimensional space. So now we have lower range to upper range, as I described here. We have just a density approximation relative to the range of values that are in the first principle. What happens with the remainder of the anisotropic information? What would we think about that in terms of if we had done this as a regression? What would we think about what is contained within the second principle in terms of the descriptive capacity of the system?
The number of times that particular value was in the data set.
Correct, right? Correct. Functionally, that spread is like a residual. What's in the second principle is what I didn't capture in the first principle. Is what was left over. It's the error that I had to be acceptable in order to make the compromise of losing the dimension. So if I was to only utilizing the first principle component, right? So I said I'm going to use the linear recombination that maximizes variance capture for both of those two original features. This is a feature or dimensionality reduction methodology, right? The goal is to represent the data as well as we can, utilizing fewer features. We did that previously by just eliminating the features. So what would happen, I'm going to zoom this out again, we're going to look at these two things together. What would happen if I simply removed ad spending, right? I say, well, most of my variance is contained within population. So I'm just going to remove ad spending. I'm just going to project the value of population. Well, let's think about a triangle, right? The length of the hypotenuse is greater than the length of the leg of the triangle, right? This is being the leg, right? Base. The hypotenuse, at that point in time, this is this capture line, the maximum linear recombinatory variance. We're only going to keep the information contained, or the variance contained within the leg of the triangle, right? It's smaller than the variance that's contained within that hypotenuse of the triangle. Thus, it is actually lower in variance. So we're going to be throwing away all of the information that was contained in that leg of the triangle. Effectively, the argument is if I eliminate ad spending as a feature, what I'm trying to look at is I'm looking to try to say revenue for companies, right? Companies' revenue relative to the population and the ad spending that they put out for that population. Let's say that this is in tens of millions or something like that, right? So if I wanted to try to just regress utilizing population towards ad spend or towards profitability of the company, ad spending seems to be a factor, right? Because there's quite a bit of difference between the way in which these companies seem to spend money on the ads relative to their populations. There's a variance in it, in the effect that saying that some systems, right, some people at 40, let's look at it from this axis, at 40 million-ish to 37 million, this company spends $10 million on ads, this company spends 22 million on ads, right? This company spends, 21, this one's 20, something like that, 17, right? All the way around this space relative to that population. This principal component is the capture characteristic where each individual point effectively incorporates both the population and the ad spending together but then characterizes them as a single feature that we can utilize for a subsequent regression or a subsequent model, such that we see the way in which the trend of the entire system moves together, right? It's actually taking and incorporating them into a joint type distribution where we see them moving with respect to one another. But as a result, I can't capture all the variance. Similarly to the fact that whenever I'm doing a linear regression, I can't capture all the variance in the data. I have a limit, an upper limit. That upper limit is the degree of flexibility of the model. So actually utilizing the linear system here for the first principle is a method of trying to stop it from doing any kind of overfitting by having too much complexity for the underlying model. Since I know it can't overfit because it doesn't have enough complexity to overfit. And since I know that I will get maximum capacity or maximum interpretability from the resulting data after the transformation, if I utilize this understanding of the first principle having the most information that can be retained from those two features, that information will be the best distribution of them, all right? And then what's left over from that will likely contain a higher ratio of relative variance in its underlying expressions. Let me show you what I'm talking about. These slides are pretty good, so I don't really have supplements here. All right, so here's the first principle component. Population and ad spending, this is the distributional characteristic of the first principle component. This is the component of the first principle relative to population. This is the component of the first principle relative to ad spending. That's pretty coherent, right? We get a good trend analysis. Here's the second principle. Interesting, right? Better one, better two, right? Notice something. Correlation's quality there. Correlation's quality, right? This is a good representation of the underlying system. It likely has a high linearity, high collinearity between the elements of the system. This appears pretty random. Could you put a regression through that? No. If we were to think about the spread over which the distance bifurcation of the values in the principle as being a width over which the values projected as a type of variance that would be due to something like noise, then I would say the signal to noise ratio of the first principle is optimized. I get more information relative to the range of values, right? What's left over actually contains more of the noise. It contains more of the process variability. From resistor to resistor, from capacitor to capacitor, the amount that they can hold and charge, how much voltage a battery has, that kind of variability in process. Most of it is captured by this underlying model first component. Most of what's here is effectively the trash. It's effectively the trash. Or at least with respect to the underlying modeling process, it has less use, less utility in its capacity to describe the underlying system.
I still find it surprisingly similar.
Why do you say that?
Well, the distribution between population and ad spending, it's like almost very similar.
Okay, you're saying as far as with respect to the way the
yeah, this has a correlation between the two, and so does the other graph. Even the trash is correlated.
Absolutely. Well, partially it's because what are these? They're rotations.
Right.
The rotations are the same matrix rotated, right? One being the axis of maximum axis of projection for the first element of the first principle, right? They're rotations. They've been
Almost
transposed, I
right.
believe. I believe that's just a direct transposition, right? So the reason why I say it's a direct transposition is what? Because it was an original rotation, then you have the effect of the distribution in ad and the effect of the distribution in population, right? Those should be transposes of the same matrix, because it's just reprojecting the first principle. Why should that seem like a good thing? Well, because we've captured maximum variance between each one. Where I said this one has less linearity, less relatability, right? So if we're looking at it from the projection or perspective of trying to model the change in value with respect to the change in the feature variable, could you utilize some form of regression on this data to get a good correlation between the change in the principal in the component and the value of the original projected space? Not really. There's nothing there. There's no real correlate. So the idea is that the further away you get from that first principle, we should see a continued level of effectively less and less usable information. So by the time I get up to, if I had 3 dimensions and I was to find the first principle of those 3 dimensions, what do? I actually could find the first axis of projection such that a linear recombination of those 3 features goes down to 1 feature. The first principle would be a recombination of all 3 of those features such that it maximizes the variance for a new composite feature that contained as much of the variance from all 3 into 1 singular projection. I would then have a second principle from there, which would be what? The residual variance in the first most useful axis that was decorrelated, the first 90-degree offset axis in that system. I would then have to go to another 90-degree offset from that one in order to pick up the remainder of that distribution, right? And by the time I'm there, I'm at my max. I'm at the residual on what's left over, right? Effectively the RSS in a sense, the trash left over from what I've already maximized in the previous system. So I have high flexibility to be able to choose which axis I'm going in to maximize captured variance. Then I have what? I'm constrained by the fact that I've already chosen that first one. So as long as I'm normal to that, if that is a vector in space, as long as I'm normal to that one, I still have flexibility to choose the best of those resulting axes. But by the time I get to that third principle, what is it? It's just what's left over, because it must be normal to the first, normal to the second. So by the time you get that last one, that is just the trash that wasn't contained by or wasn't described by the first 2. So if it's the least correlated portion of it, it's the least, it can capture the least variance, then it probably contains more of the factors that were noising and corrupting and creating process variability in that original data set. We tend to say that if I maximize the variance capture in the first principle, I'm capturing mostly data, right? I'm capturing mostly informative process. Second principle should be still relatively informative. But what happens is this falls off for each component. The amount of information relative to that principle drops, right? 75% might be in the first, right? 15 might be in the second, right? And then the last one is that 4 or 5% that's left over for the system. Yeah.
So this is me just trying to correlate between like the lab and what we're doing here. So in the lab, when you had us do like the forward and backward selection, within however many asterisks there were in each variable, the top 2 that we choose is essentially going to be the first and second principle, where everything else
Kind of. But here's the thing. They're whole features.
Right.
It's just throwing out the additional axis, right? If you were to project it in higher dimensions, it doesn't capture the combination of them. It just captures, you're just keeping this feature and this feature, right?
Right.
If I do a principal component, I get to keep a new feature, which is the byproduct of both of those features put together. These actually kind of mean nothing, right? They're kind of unitless because they don't really represent the actual value of either population or of ad spending. They're a recombination, they're a new feature, right? But because it's a transform that just requires a rotation of the existing data, it doesn't actually change the way in which the points are correlated with one another. Thus, it is informationally preserving. It's an informationally preserving, informationally maximizing conservative transform, right? But it's not destructive, it's not fully destructive as the other forward and backward selection processes are. It doesn't throw out the whole feature. It incorporates as much of it as it can, right? So what we want to do is we want to choose the first few principles. I'll actually show you guys an example on Monday of what this looks like with the Fisher iris data. We'll go through all the principles of the projection of that 4-dimensional space and see how each one captures and what the level of capture is. And then we'll try out another higher dimensional data set from that point. So did you have a question, Mark?
It's just I think you answered it. I was gonna ask before he asked his question, if you could use this to get rid of some of the data that is noisy to get a better model.
Correct. The whole point of this is that previously we've made arguments to say stuff like the bootstrap or whatever wasn't really useful for modeling. This is 100% useful for modeling. But the consideration is something that's kind of hard to deal with, and that is that once you transform the data, you're stuck with that transform forever.
You can't
right?
go back.
The other thing that you also can't do is, let's say that you do a feature reduction via a sequential forward or backward selection. Let's say that I had a big data collection that required me to collect all the individual, like I had to ask you 20 questions in order to get your data set, right? To collect 20 features from you. Let's say that I only found that the top 3 of those features were really necessary. Then I don't have to worry about collecting all 20, I can just collect those 3. What happens with the principal component? I always have to collect all 20 because there's a possibility that some tiny fraction of the deviation in that principal projection captures a little bit of the information from vector 20 or from feature 20, right? So I would always have to collect and always have to have the same dimensional input to the system. So I can't utilize it to really characterize which features are the most important from that system in some sense. It's actually kind of hard to work back to what was the most important as you go up through the principles. It's a problem. I've worked with it a lot. I had people that went through a PhD program that were utilizing PCA projections for large-scale data sets, and they weren't able to preserve that informational characteristic. You can't say which feature is essential and non-essential by utilizing PCA. It doesn't quite work that way, right? So if you're going to always get that data, you can utilize the PCA to describe the features and only use the first 3 principles. That will radically reduce the complexity of your model and still improve the quality of your output. But it doesn't reduce, or it doesn't tell you which of those features are most important per se, and it doesn't necessarily reduce the computational overhead of collecting and then processing the data. So if I get a new sample, what do I have to do? I have to apply the same principal component transform to that new data, and then pull the features out of the new transform version in order to be able to evaluate it with the model. Because I can't take the original data points and plug it into the model. And I can't take the model and try to inverse the transform of that system back to reproject to the original data points because it's not necessarily preserving of the dimensions. See you guys next week. Have a good weekend. Thank you.
This stuff is so...
It's just simple. What was your problem?
It's just no...
I'm just kidding.
I'm used to, give me a high-pass filter. Here, well, here's a high-pass filter. What parameters do you have? And this is just, there's no, like...
Get your canvas pulled up?
Yeah.
Pull your canvas up. I want to see what you're talking about, because I didn't look at it.
Oh, mine looks like his, so I'll let him do it. My computer's already off.
Was this? Is this like the...
This is that quiz we were talking about where it shows like a grade on the outside, but when you click on it, you can actually like push take quiz.
Are there any other values in it?
Yeah. It tells you like out of 100 what the score is, and then when you click on it,
I
it
might
lets
have,
you.
I might have a serious problem. I have a serious problem. I might.
I mean, I can show you on my
If people
tablet.
go and start taking it, thinking that they're going to be able to retake the midterm because they're taking my midterm from last semester, that's not what it's supposed to be.
So I come in here.
I told him to report the
Click
scores. I
on
didn't
assignments.
sign.
And
I
it
know
says
exactly what you're talking about. I get it.
midterm. And then it tells me this, but it also says I can take the quiz.
Yeah, I just get a alert saying that if you quiz.
Oh,
Yep,
yeah,
that's
I
a
got
I got
problem.
Canvas alerts.
An hour and
it also
15 minutes.
emails.
You're gonna fail now. It's gonna rescore.
I will just drop the existing scores and delete this.
You got 74 minutes to do 30 questions. Or
Don't touch it.
Okay.
Don't touch it. I will reject all the scores. I don't know what people are thinking. I don't know what.
Yeah,
I don't know. That's not what I intended. There's another quiz that I put up.
Oh, okay.
That's just it's just a topics quiz for the, and you guys can't see that one?
No,
No.
this is it. That's all I can
We
see.
can see. So I just last night I said, what? Can we take that again?
Every time I ask him to do stuff for me, it just ultimately makes up more work. I end up really just, basically, I should just do it myself. So, I'm getting a new TA next semester, which will be nice. I don't dislike the guy, he's good people, he tries, but he doesn't know enough about Canvas, and I'm telling you, I get really frustrated that the department wants to have us hire people to do grading, but then they don't want to train people to use Canvas.
Oh, so they don't
He could
train?
have looked,
No.
he could have looked and saw that that was a quiz,
Mhm.
but he decided to just start adding in scores to it, which meant he published it.
Yeah.
He would have had to publish it to add scores. That's not supposed to be published.
Mhm.
So that's from last semester, something I imported from that previous score. If I have people now that are gonna be coming and saying, oh, I got this on this score,
Mhm.
now I have to deal with that. So I gotta get back to my office right now. I'm sorry, guys. I'm
No,
sorry,
no, you're
you know,
good.
Yeah,
it's
yeah,
a-
you're good.